All right, so hello students. This is the second half of the course on orbital mechanics, which you all have signed up for. Um, Unfortunately, due to circumstances outside our control, we cannot meet on campus, and so I'm recording these lectures. This is the first lecture in the second half of the course, starting with Lecture 11, Rocketry. So hopefully, since you're watching this, you've figured out how to access these videos, so that's good. Today, we're going to be talking about um, how to achieve the delta V's that we use to get into orbit and to maneuver around in space. So a little bit of an introduction to rocketry. Now, I apologize. I don't have quite all the technology that I really need to be presenting this course, but that should hopefully follow in the next lecture. I should have that by Wednesday of this week. So the next lecture should have a little bit more advanced technology. So hopefully you can hear me all right. I'll get a better mic hopefully by Wednesday. But in the interim, hopefully this works well for you. All right, so I got my primitive tablet here, and I'm going to be making notes as we go across, so I can make notes. So let's see. Hello. Yes. Right. So let's go on to the first slide. So I apologize that those of you who were in class prior to the spring break, and some of this, in fact, most of it, should be a little bit of a repetition. So I apologize for that. But I wanted to start fresh from the second half of the course, so that the videos sort of were continuous. I know we dropped off at slide 20 or 18 or so before the spring break, but maybe you've forgotten all that, and certainly with all that's been going on, I could not blame you for that. All right, so what is the goal of this sort of mini diversion, this subunit, if you will? I forget which lecture this corresponds to in Prussing and Conway, or in Curtis, but it corresponds to one of those chapters. In most courses in spacecraft dynamics and orbital mechanics cover this, so we're covering it as well. And it's important because it gives you some intuition into what is possible with delta V. We've talked a lot about delta V and maneuvering in space, but this gives you an idea of the limitations to what is possible with those kind of maneuvers, and specifically the great cost it creates to achieve delta V in space. We talk about kilometers per second for delta V maneuvers. Well, that requires a great deal of propellant, and the question is how much propellant, and how much propellant is feasible really to get into orbit. Obviously, we've sent spacecraft outside the solar system, so how did we manage that? Well, with a great deal of cost, of course, and not a lot of payload. So we'll cover some of those concepts here. So specifically, delta V is created by mass ejection, basically, conservation of momentum issues. So how much mass does a rocket need to have in order to get a certain delta V out of it? So we'll talk about that. That underlines everything we're going to be talking about. So mass consumption. It's governed, right, by this concept of specific inflow. So the faster you can spit mass out the back of your rocket. So let's see, here's your rocket. Oh, it's a terrible rocket. So here's your rocket. Here's your, you spit mass out the back in the form of propellant. That makes your rocket go forward, right? And so, of course, the faster you can spit mass out the back of the rocket, the faster your your rocket's going to go the other direction. So this limit on specific impulse is sort of a code word or terminology or something for the speed at which propellant is being spit out the back, right, is limited by the type of rocket that we're using. So we're going to be talking a little bit about the various rocket types and what kind of specific impulses those are capable of producing. And that's basically determined by your propellant type and also a little bit by the design of the rocket, so nozzle types and so forth. So we'll talk about a little bit of that. And we'll find out, ultimately, this has been an issue for a long time, that there are limitations to those, to what we can do. So most specific impulses, right, that the speed at which we can spit out fuel out the back, most normal rockets, right, that speed is limited to about 3,000 kilometers per second, right? Or wait, 3,000 meters per second, sorry. So 3 kilometers per second. So what then can we achieve with those kind of speeds? What kind of limitations does that put on our rockets? And then we'll find out that those limitations are actually rather drastic. People have been very concerned about these limitations since the times of Hohmann and Tsiolkovsky and all these guys. So we'll talk about a little bit of that, and we'll talk about how to overcome some of those limits through the use of staging. So that's where structural mass used to support to carry this propellant. That's the main limitation, and staging is a way to overcome that to some degree. So we'll talk about what that means. So the basic problem that we've got here, right, is this one. We have a dry weight, that's a payload, right? This is what we want to launch into space, 30 kilograms. And the basic question, that you need to ask before you do anything is just how much propellant do we need? How big a rocket do we need in order to launch that 30 kilograms into orbit? Now, it turns out the answer is quite rather a large one. And actually, without staging, we'll find out that it's next to impossible to launch anything into space. So basically, the question is, do we have 30 kilograms? We want to launch it into space. We want to put ourselves in a circular orbit. Very minimal circular orbit, say of 20 kilometers altitude. And how much? What are the limitations? How much payload do we need? How much how much structural mass? How much propellant do we need to achieve that? So that's the topic of this lecture. So let's get into the basics. All right. So this is basically what I've already been talking about. We've talked about delta V as sort of instantaneous thing that is created. And so in the following slide and the slides following that, we'll talk about how we achieve this instantaneous delta V. That it's not really instantaneous, but the rate at which it's created doesn't matter too much in terms of the magnitude. But we'll talk about that, and then of course, right, how much it costs us in terms of the weight of the rocket, the dry weight, the weight on the launching pad, or the wet weight, the weight on the launching pad. Okay. So we talked about the delta V's in space, right? And there's quite a few we need. So for example, if we want to put our satellite into a geosynchronous orbit, that's what GEO is. Oops, stop pushing that button. That's what GEO is. Then remember from the Hohmann transfer, we maybe need a 2,400, 2.4 kilometers per second burn at perigee to get us up to achieve that geosynchronous orbit. or to get to the altitude we need. And then to insert into that orbit, we need another delta V when we get there of, say, 1.5 kilometers per second. And maybe we need a plane change, for example. Then that adds a little delta V budget to our system. So overall, this is about 4 kilometers per second is the requirement for inserting anything into geo, and that's in addition to what we need to get up into sort of a parking orbit, which is also fairly high. It's about 9.8 kilometers per second just to get us into parking orbit. So that's sort of a basic delta V requirement. So 9.8 to get us into orbit, and then an additional 4 kilometers per second or so to get us to geosynchronous. And remember, geosynchronous, right? If you remember that map of the delta V's, there's Earth, there's geosynchronous, here's the moon over here, right? The home and transfer delta V's to get us into geo, right? 4 kilometers per second. That's approximately the same delta V needed to get to the moon, right? That's approximately the same. So I apologize. Hopefully, when my better technology comes around, these lines will look a little less, how should I say, sketchy, right? In addition to that, right, we have like different delta V budgets for in-space maintenance. By the way, these tables come from the SMAD tables, Space Mission Analysis and Design, a book which is no longer, for some reason, in print. Hopefully, at some point, it will come back in print, but rather hard to get at the current moment in time. So up in orbit, right, low Earth orbit. That's what LEO is, low Earth orbit. We have some delta V's, even if we're not going any higher than the low Earth orbit. And the 9.8 kilometers per second is what's required to get us into low Earth orbit. So there's some drag up for atmospheric drag up in the orbit, and that typically eats up delta V budget, depending on your altitude, of course. We'll cover that later. So that can add to your budget. You need to add some delta V to your budget in order to not become space junk at the end of your mission. So that adds a little bit to your orbit. Also, if you don't want to go to home, and you can escape, go to Mars or whatever, and that's this number. So again, notice that the delta V requirements for escaping Earth's gravity well are approximately the same as that of getting to the home and transfer, getting to geosynchronous orbit, the home and transfer to geosync. So again, these numbers are fairly rigid, right? We need about 4 kilometers per second delta V budget once we're in orbit to get somewhere, almost anywhere of interest. In addition to that, there's some onboard maneuvers that we need to take into account. In addition to drag, we might need D-spin, right? If we have a spinner, spin control. Spinning satellites are less common these days, so we're not going to focus on that too much. We'll talk about when we get into satellites what these things are. Let's see. I can try my eraser. Where did my eraser go? Oh yeah, that's right. I have an eraser right here. So then, yes, orbit correction. You have to calculate something for that. Station keeping, right? There are a lot of orbital perturbations. Again, we'll be talking about that in a later lecture. You need to correct for evasive maneuvers. Okay. So that's if you've got someone coming to get you, or you got a micrometeorite coming in that you want to avoid. Sometimes you need delta V for that. Attitude control, especially with 3-axis stabilization, can be a significant contributor to propellant mass. it's not as much as delta V typically, because we often use like Hall effect thrusters or PPTs for attitude control for these low, when we have electricity and we don't need a great deal of thrust. It's sort of distributed over time. But we include it here anyway. So this is acquisition. That's if we have a star tracker or an Earth tracker or a sun tracking attitude control system, we have some delta V to get into the correct orientation. If you have a spinner, right, precession controls, you need to dump momentum. If you have a reaction wheel or the gyros, the alternative to momentum wheels. And then, of course, if you're 3-axis stabilized, right, delta V, you can use delta V directly for 3-axis control without the momentum exchange devices here. So, okay, so that points to ultimately a lot of delta V to get up into orbit and a lot of delta V once you're in orbit. So a lot of delta V. So how do we create delta V? So before we talk about the delta V's too much, right? I want to get some idea of what the rocket looks like. So that, right? This is important because when we talk about initial and final weights, we talk about the rocket equation, right? We're going to be talking about the ratio of lifted mass, so that's payload mass, to total mass, right? Again, apologize for the sort of sketchy nature of this. So that's mt naught. That's the initial mass before you do your burn. And then the final mass, which is depending if you count for structural weight or just the payload, right? That's m naught, mt naught. So we typically refer to the dry weight and the wet weight. This is a single stage rocket, of course. We'll talk about multi-stage rockets later. But we have a dry weight, which is what happens when we burnt off all our propellant. I guess that assumes a liquid propellant, but once we get into above the atmosphere, those upper stages, we typically talk about liquid-fueled rockets, and so that's hence the term wet weight. And so the wet weight is the weight with the propellant. So the propellant is water or something. It's not actually water, although often it does turn into water. But the wet weight is the weight with the propellant, and the dry weight is what happens once all the propellant has been expended. Right? So whether you include structural weight or just payload weight, that depends. We'll talk about both cases. In real life, of course, we always have structural weight. So it's broken down here in these SMAD tables, right, into stages. We're sort of going from bottom to top here, sort of the opposite direction. So stage 5 is the payload performance capability. So that's basically what these systems can lift. So the boosted weight is that's whatever the rocket system says it can lift. That's what it lifts. It has a little bit of performance margin built in there. So you add injected, so that consists of injected weight plus booster adapter weight. So there's like a little adapters here, right, to attach the top of the rocket to the bottom of the rocket, and you can really include that in structural weight. So we'll consider that part of structural weight. So we have all of this stuff, right? And then on top of that, right, we have the upper stage, right? So we can think of the payload as the upper stage. Now the upper stage, right, Centaur upper stage, something like that, also has propellant, so we can think of it as like a separate stage. But we're thinking about sort of one-stage rockets here. But again, this upper stage weight is here, and above that, attached to that, is the spacecraft weight, right? And then we have the again, this really the top of the rocket here, the dry weight, the weight of the spacecraft itself, the thing you want to launch. So that's the design planning stage. You want to add a little bit of buffer to that. But when we talk about dry weight or payload weight, this is really what we're talking about, the payload weight. And then there's, addition to that, there's a wet weight for the payload, which is the payload, again, those delta V's we talked about on the previous slide that require propellant. So this whole thing here, right, we can really consider M naught. Okay, so again, those are the sort of this is the very basics of what a rocket looks like. Right. Just to give some examples here, right? These are staged rockets here. We have there's a very old picture, 1962 here, which illustrates the how these rockets work. Basically, you have rockets on top of rockets. So this is 1, 2, 3, 4, 5 stage really a rocket here. So there's the first stage. It's a rocket. Its payload is everything above it. There's a second stage. Once you've ditched the first stage, its payload is everything above it. This one's payload is everything above that. So M naught. This stage, right? Or this rocket here, right, has a payload which is be careful here, right, which is everything above that, and then we have a separate payload here, which is everything. So lots of rockets stacked together in a multi-stage rocket situation. And then we have these various masses. So again, that's here, right? We have sort of M naught, right? This is the payload mass, right? And then some structural mass associated with the previous stage. So this is a single stage rocket. So every stage has some structural mass associated with it. That's sort of the whatever weight this the steel and the nozzles are for each stage. That's the structural weight of that stage. Right? Obviously, in the ideal case, we'd have very thin upper stages, very thin structural mass, but that's in reality not typically the case. We'll talk about these ratios a little bit more in the lecture. The propellant mass ratio, payload ratio, and the structural coefficient. So the structural coefficient, we'll talk about it more later. It's specifically sort of the limitation on each of these stages, how much structural mass you need for each little bit of propellant mass. So this is kind of a law of nature, if you will, right? By contrast, right, this light rate payload ratio here is you can optimize it a little bit. So you have obviously your payload is typically fixed, and then you can adjust the size of the stage compared to its payload, right? So that's lambda. You get to choose this. Yeah. Red, obviously, it's occupied a little bit here. So we can play with lambda. Structural coefficient is sort of again fixed. We don't get really to choose this. We can only choose lambda. And then this propellant mass ratio is in a single stage rocket. It's the mass of everything, right, divided by the mass of what after the propellant's all used up. We're not going to focus on this number too much, right? Let's put X here. Right. Not going to. That X is really quite large. Okay, make it smaller. Yeah, I'll just get rid of my X. Okay. So armed with that, let's talk a little bit about the dynamics, right? The dynamics aren't terribly complicated. So how do we create delta V? So ultimately, if you've got a very simple rocket, is modeled here as a cannon, right? We've got this is the rocket. Mass of the rocket has a mass, and this is the propellant, right? So if you shoot the propellant out the back of the rocket at a velocity, which we'll refer to as the exhaust velocity, or VE or C, depending on which number you're using. Then, if this particle has a bit of mass, and it's spit out with respect to sort of inertial reference frame out of the back of the rocket at velocity c, that gives it some momentum, right? And by Newton's laws, which law is that? Second law, conservation of momentum, right? The momentum in this direction, momentum is a vector valued function. The momentum in this direction of the propellant has to equal the momentum change of the rocket in this direction. So the rocket moves that direction with a delta V. And so really conservation of momentum is really just mass of rocket times delta V equals mass of rocket, mass of propellant times C. It's not quite that simple, but that's more or less what it is. So we have the before and after here photos, right? In here we've got the total mass of the rocket propellant system, right? Mr plus MP, right? The propellant is contained in the rocket. It's moving that direction with a velocity v initial, right? Or v in this case, and that's the momentum before firing the cannon. So the after firing the cannon, right? The rocket has a velocity v plus delta v, and the propellant has a velocity v minus c. So the propellant is going in this direction. The whole system, the inertial frame, right, is moving with a velocity v. So that's hence the source of v. So the total momentum after firing is the system is the mass of the rocket, v plus delta v, plus the mass of the propellant, v minus c. Right. So actually, I should probably label this as delta m, the mass of propellant or delta m. So from conservation of momentum, right, we know that the total momentum before equals the total momentum after, and so we can just say this equals that. Write down that equation. And, well, everything here is known. Delta M is known, V is known, MR is known, all this stuff is known. And so all we need to do is solve for delta V. And if we do that, we obtain delta V is delta M times C divided by MR. So that's basically what we had just right off the bat, but I'm being a little bit more rigorous here. So what does this tell us, right? It tells us, first of all, right, that the delta V for a single particle of propellant, right? So this can be small, right? infinitesimally small, of course, if we're spitting out lots of tiny particles of propellant. Right? So the delta V to a single, the infinitesimal delta V corresponding to an infinitesimal particle of propellant is the mass of that particle, times c, that's the exit velocity, the exhaust velocity, divided by the mass of the rocket, right? So you can't change this much, right? We would like to maximize that, of course. A small problem, of course, is that actually, in order to make this number large, we actually need to make this number small, right, with our propellant. That's why propellants that use light elements, so like hydrogen and oxygen, well, oxygen is not very light, but hydrogen is, tend to have a larger C than heavier elements such as solid rockets, which have these sort of metallic components to them, heavier elements in them, heavy metals. But that's something we'll discuss again in a bit. So again, I don't think there's anything new here, right? So that, again, this is for a single infinitesimally small particle of propellant, and it's not really the equation we use. This is not the rocket equation. This is a single particle propellant. You have to spit out a lot of propellant in order to get a reasonable delta V. So we'll just take these as delta m's, and we'll use calculus to integrate this equation in order to get the total delta V for a lot of propellant, basically. And essentially, that's what the rocket equation is, right? It's the Sikorsky rocket equation, right? It assumes continuous thrust, right? If you look at this picture here, right, I don't see any cannonballs being shot out the back of this rocket, right? There's lots of particles, and they're all delta m's, and it's continuously throwing them out, right, throughout the delta V burn, right? So we're taking these as infinitesimally small particles of propellant and infinitesimally small delta V's. Right? We take delta V and this delta M, right? So very good. Dividing by the whole thing by delta T, right? Delta T, dividing both sides by delta T, we get delta M over delta T on the right and delta V over delta T on the left. And so we take those terms to be V dot and M dot. Okay. So V dot is a function of M dot, the rate at which you're spinning propellant out the back, times the exit velocity of that propellant, divided by the mass of the rocket. Now this will be decreasing over time, right? That'll be decreasing over time. This number is more or less fixed, right? You can see that we're not reducing our thrust. The thrust isn't throttled. You can throttle the thrust over time, but it doesn't really help you at all, increasing it or decreasing it, unless you're like low in the Earth's orbit, in which case you want to like dump propellant as fast as possible to get out of, to not have to fight gravity. Talk a little bit about that later, but for now we'll just assume a constant mass flow rate, m dot. So if we integrate this equation, right, taking differential form, getting rid of our delta t's, we have delta m on the right, integrating this equation from initial state to final state, integrating over time. This 1 over m, right, this is a function of time, remember. The integral of 1 over m is natural log, right? And so we integrate it from initial time to final time, and so that becomes CLN, m t naught minus CLN m tf, right? And then using the property of natural logs, we just that becomes division inside the argument. So this is what we get here is essentially the rocket equation. assuming a constant mass flow rate here. Well, we're not fussing about mass flow rate. And this is what we get. The delta V produced is linear in the exhaust velocity, so faster the exhaust velocity, the better. Times the natural log of the initial mass, right, divided by the final mass. Right. So the ratio, essentially, of the initial mass to the final mass determines the delta V. Right. So that's why we talked quite a bit about these masses in the previous slide, because this initial mass, right, that's the wet weight, right? It's the mass of the propellant plus the mass of the structure plus the mass of the payload. And I think we occasionally used MD for that. Whereas this, the final mass, is the mass after you've used up all your propellant. So it's just the mass of the structure plus the mass of the payload. So if you remember our rocket here, we had MD. Below that, we had MS. And here we had MP. That's sort of our schematic of a rocket. And so the ratio of this number to this number is what determines our delta V. Okay. So natural log looks something like that, like really flattens out. So if this is, if we plot this, delta V versus this ratio, M naught over M final, right? Yeah, okay, I'll just leave that. Then to achieve the higher your delta V, right, the smaller this, the larger this ratio has to be. Okay. So to achieve really large delta V's, you've got to have really small payload and structural weights. So we'll talk about the limitations of that later. Now, don't of course use this equation we talked about before, right? For the infinitesimal delta V, that's not something we want to use. That was just used to derive what is actually this, which is the rocket equation. Okay. So let's see what I'm going to say. Yeah, so that's the rocket equation. Again, the mass flow rate is the rate at which we're using up the propellant. It doesn't ultimately affect delta V as long as it's constant. However, if you want to achieve that delta V in as short a time as possible, you typically want to use it up. You make that large, right? So the first stage is to typically have a very large mass flow ratio. Again, this mass flow ratio can be throttled in both liquid and hybrid rockets, not for solid rockets, but for liquid and hybrid rockets. And so again, for that first stage, we typically want to make it as large as possible so that the delta V happens quickly. Once you're in space, actually continuous thrust rockets are actually typically much more efficient because they can use electricity for thrust, but we'll talk again about that later. Okay. So let's examine this rocket equation a little bit. So here it is. We have an expression for delta V as a function of wet and dry weights. So again, don't confuse MT naught and MTF with empty and full. That's not. This is actually the full weight, right? And this is the empty weight, or after propellant. So it's a little bit confusing because there's an F here, which you might think means full, and this is a 0, which you might think means empty, but that's not it at all. It's the initial and final times, right? That's what we're talking about here. So again, right, here we go. This is the so for a given delta V, right, in order to achieve that delta V. So if we invert this equation, we say E to the delta V over C equals MT naught over MTF, right? We can then solve for the change in delta M, right? Propellant mass as a function of the total mass. So propellant mass is a function of total mass. So for any given delta V, we can achieve that delta V for, we know how much the fraction of propellant needs to be to the given rocket, right? So what we see as the delta V increases, right, this fraction gets very large. It gets very close to 1. So we need more and more of the rocket to be propellant, right? So if you have, like, in some cases, right, if this is like a popsicle rocket, a pop rocket, I guess. There's a little stick there. If this is a pop rocket, right, and we don't need any structural mass, we can just, lost it there. An increasingly high fraction of the rocket propellant, and then we just have our payload here at the top. So in theory, right, achieving any desired delta V is possible for this, but that of course neglects this structural weight. The problem, of course, is the structural weight. The more propellant you need, the more structural weight you need, and the structural weight contributes to whatever goes here at the tip. And so in practice, right, you cannot achieve arbitrary delta V's just by increasing the mass of your propellant. So we'll talk about that in a bit. So the equation, again, the rocket equation, right, is actually a relatively old equation. It's been known for some time. It's just integrating the Cannon equation, if you will. It was introduced by Tsiolkovsky back in the day. It was one of those crazy Russians who lived back in the day. And I hope not many crazy Russians are watching this, so they won't be offended. But he was one of these guys who lived in a recluse, who lived in a log cabin, worked on math, I guess, I don't know, outside of Moscow. Did lots of space stuff. Not quite the same as Hohmann, but also an idealist. And incidentally, of interest to us, right? He also was the first person to think of, conceive of the idea of a space elevator. Space elevators, of course, combine centripetal acceleration with use centripetal acceleration to get up into orbit to launch things as well. So again, space elevators also have the idea of a space elevator dates all the way back to, again, the time of the invention of the rocket equation. So it's again also a venerable old concept. Of course, the rocket equation has found many more uses than the space elevator, and of course, I forgot to mention. Why are we? Sorry, I seem to have lost myself. Must have pushed home or something. There we go. Yes. So the space elevator, again, inspired by the Eiffel Tower during, I guess, one of Tsiolkovsky's visits to Paris or something like that. Build it large enough, and you can put things into space without using the rocket equation. So alternative means of transport there. So again, right, so we've talked about the limits of the rocket equation in terms of m naught over mf. Now we'll talk a little bit about the other part of that, right, the rocket equation, which is this c term. Now, c, the exhaust velocity, or the speed at which you spit propellant out of the back of the rocket, is, of course, in some ways more important than this ratio. If you could spit propellant out the back fast enough, you can overcome any of these ratios, right? This is a much more direct way of increasing your delta V's. Unfortunately, physical limitations of nature prevent us from playing around with this too much. As we'll see when we'll talk about rocket types, that you can get something out of that. But to understand a little bit, where the C comes from, I'm going to talk a little bit about rocket constructions, throats, nozzles, aspect rate, area ratios, that kind of thing. Not in too much depth, because that's a different class. It's propulsion. But I'll cover the basics here, just so we know what we're looking at when we look at rockets and why they're shaped like they are. Right. So basically, in some ways, this is the C is created by the fuel, right? Right. Whether it's gasoline or hydrogen and oxygen, right? Whatever it is. It combines in the combustion chamber, it burns, it creates a relatively high temperature. I think this is a TE, but T combustion, let's say. Very high temperature, right? Creates very high temperatures. And of course, pressures. We have very high pressures. Now, if you just have a balloon, of course, a balloon rocket, right? You don't actually need high temperatures to create thrust, right? You have just some pressure there. So you have a balloon. You put some pressure in the pressure chamber. It'll force the propellant, in this case, air, out the back without any temperature change at all, right? But of course, it's very ineffective. In fact, generally in rockets, we want very little exit pressure, and for a reason I'll mention in just a second. But if you have cold gas, there's a cold gas thruster. Did I spell balloon right? I don't know. Maybe 2 L's. Right. Cold gas thruster. You're working entirely with this exit pressure, essentially. So there's two components to this rocket. This is something that's really quite tricky, and when you take your propulsion class, you'll learn a great deal more about it. The exit velocity, right? This VE, exhaust velocity. That's really what we're trying to maximize. Now, the bump we get in delta in C, the sort of the effective exhaust velocity, the effective velocity, right? Highlight that term. The effective velocity C, right? Now the rockets are not generally rated by effective velocity. They're really rated by ideally expanded nozzles. But for now, we'll talk about effective velocity C. Okay. Is determined by the actual velocity of the propellant, right? That's actual. And then you get actually a boost for having not fully expanded nozzles, right? You get a boost if your exit pressure is greater than your atmospheric pressure, and that's sort of like this balloon example. So the pressure at this exit is multiplied by area to get you a little extra force, right? Pressure times area gives you force, right? And of course, the amount of mass flowing through also contributes to that. But this is a little bit misleading, because this is not helpful. Why is it not helpful? Because it turns out, right, that that pressure at the exit, right? Well, that pressure is created by particles bouncing around randomly, right? And particles bouncing around randomly are not bouncing out the back of your rocket in a sort of organized manner. And so once you have these particles bouncing around randomly here, oops. right? Once you have these particles bouncing around randomly right here, well, they're like, they can go that direction, they can go that direction, that direction. They're not the cannon ideal that we'd like, shooting straight out the back of the rocket, which is what we want. So exit pressure, whatever exit pressure you have, is going to degrade the actual velocity of the propellant out the back of the rocket. So there's this trade-off between pressure and exit velocity. And we want to come down firmly on the side of exit velocity. So it's good. Exit pressure is generally bad, right? Because it's disorganized motion, right? So how do you actually minimize this while maximizing this? Well, that's what rocket nozzles are all about, right? So this is the nozzle. Okay. So nozzles, right, organize the motion of your gas, right? If you want to think about it that way. So you create, so the particles go over here towards this throat, right? That's the throat. They come over here. They get compressed into very high pressure areas, right? They're forced out through this very energetic motion, Brownian motion of the temperature. The temperature is Brownian. They're forced into the nozzle, into the throat, and then as this nozzle becomes larger, right? As this nozzle becomes larger, and as they pass out that throat, they bump up against this this nozzle, right, and spit out the back, right? They bounce off it, impart some momentum to this nozzle, and this is where all of that momentum exchange is occurring. They're pushing against those particles are bouncing here and pushing against the nozzle and bouncing out the back, and then finally, the bigger and bigger you make this nozzle, right? The more and more area those particles have to push on, right? So the bigger your nozzle, or the bigger the exit area of the nozzle is, right? The flatter this thing, the more these particles are pushed out the back in an organized manner. The more surface you have to create force on or momentum exchange on the rocket is, the more organized your particle velocity will be coming out the back. So there's this trade-off. Actually, you can get in atmosphere. It's not quite that simple. In atmosphere, there's atmospheric pressure. That's atmospheric pressure. And so if you actually decrease the pressure too much, so as these particles become organized, right, there's no longer that Brownian motion. And so the pressure drops, right? The exit pressure drops. So there's this idea of overexpanded nozzles. So if you drop the exit pressure too much, there's actually a back force, sucking the rocket backwards due to this the difference between atmospheric and exit pressure. So that's a bit of a problem. But generally out in space, of course, the atmospheric pressure is zero, right? So we don't have this effect. So really when we talk about space rockets, right, rockets acting out in space, a general rule of thumb is we want the this ratio of the area of the exit area, right, to the throat area, right? Let's see what I got here. Okay, this the ratio of the exit area to the throat area to be as large as possible, because the larger it is, the more time that the particles have to push, and the more organized they become. Okay. So when we talk about, again, coming up, right, we talk about different rocket types and how they determine the exit velocity. They will essentially assume you're in space and that this ratio equals infinity. Right? We'll in those rating systems. And we won't talk at all really going forward about this. We'll assume perfectly expanded nozzle. But when you have staging, your first stage is an atmosphere, and so actually the first stage will not typically have the same infinitely large exit ratio. And so you do have to take that into account. Okay. So I think, so for example, these upper stages, right? This is an upper stage, right? Upper stage, right? These upper stages really have very large expansion ratios. So for example, the Merlin Falcon Heavy upper stage rocket has an expansion ratio of 117 to 1, so it's very large. Okay. And again, just to give an example, the liquid propellant rocket is rated at rather actually high for liquid rockets. The hydrogen-oxygen propellant is rated at 4.4 kilometers per second, typically. Right. So just to illustrate this, I've got, so this is, I have to open this separately. So that's the Saturn V stage separation. Right. So in this illustration, what we got here is the Saturn V rocket. So this is the launch. Saturn V rocket. Actually, let's see upper stage. Oh no, actually, hold on. This is sorry. This is not the right video. Go away. Right. Okay. So let me just mute that for a second. So this is the Saturn V first stage launch, part of the launch. Let's see, it's 3 minutes, so we'll accelerate it a bit. Oops, I guess I accelerated too much. So you see it launching out, and notice here at initially, right, you have these nozzles here which do not have huge expansion ratios. Do not have and yet when you see the propellant coming out the back, it's coming out straight. Same with the ICBM we saw in the previous picture. The propellant is coming straight out. There's no expansion, no the velocities are focused straight out the back, right? The motion, the particles are very organized. They're shooting straight out the back, which is really what you want, right? To create the ideal approximation of the cannon, so to speak. But then as we get up into higher atmospheres or lower atmospheric pressure, we do see some problems with that, the rockets not being ideally expanded. So you can see as we get sort of farther out here in the atmosphere, what we see is is some of that gas escaping to the side, right? And that's inefficient, right? That's inefficient use of our propellant when this gas escapes out the side. Not organized motion, and that just means that these rocket nozzles are not ideally expanded for these higher atmosphere burns. And that's of course why we have the nozzles for the upper stages are going to be sized differently than for the lower stage. And you really see this disorganized nature here when we get high in the atmosphere. These particles are going off to the side, and that's just not useful momentum. This side momentum is just not useful. And so we can see that more clearly to go on. Getting very overexpanded here, or underexpanded. And I think that's about all I need to show. Yep. Here you can't see it as well. So there's a separation, stage separation. Where is the stage separation? There it is, so stage separation. And goodbye to the old first stage. And then we have these new, try to track it, the second rocket, if you will, which is much better expanded because we have no atmosphere at this point. Just close it up. Right. So how fast can we spit propellant out the back of the rocket? And it depends on the rocket type. So this is typically measured in specific impulse. So it's measured in specific impulse. So it's measured in specific impulse, right? Which is jargon, really. It's the ratio of impulse, right? So particle delta m, right? This is basically the momentum of the cannonball divided by weight, right? Of the propellant on Earth, right? So weight, impulse, momentum imparted to the rocket divided by weight of the propellant. If you work out the units, right, in seconds, the units are time, right? So specifically, if you want to think of it that way, specific impulse units in seconds, right? So this is typically like, say, 300 seconds. The 300 seconds, you multiply that by 10, basically, and you get the exit velocity in meters per second, and then we convert to kilometers per second, right? So if you want some intuition into the 300 seconds, you can think of that as it is the time that propellant can lift its own weight before it burns out. Can produce basically its own weight in thrust. Can thrust its own weight. So the time it can thrust its own weight. So for example, if you have a 300 second specific impulse, like a rocket composed entirely of propellant could hover for 300 seconds. That's basically 5 minutes. Of course, it would waste the entirety of its propellant. And so that's why, of course, first stage rockets want to dump propellant as fast as possible so they don't have to actually hover, right? The time a rocket spends hovering is entirely wasted propellant, right? And so if you used up all the propellant, you could maximum hover for 5 minutes. Right. So typically we try and get up and turn over to the side as fast as possible so we're not fighting gravity anymore. Right. So you don't want to burn perpendicular to gravity because that thrust is all wasted. Right. So you want to get on your side and thrust perpendicular to gravity so that that force is no longer wasted. Right. So you want to do that as quickly as possible, preferably within a minute or 2 minutes. In any case, so this ISP is determined by the rocket type. As I said, like balloons, right? Cold gas thrusters have very low ISPs because the motion is really quite disorganized. And so you're not getting a whole lot of thrust per mass. Solid rockets do better in the range of 300 seconds to 280. Liquid propellants do better than solid rockets in general, but not much better, you can see here. Like even the very best liquid propellants, which is H2O2, right, have ISP of about 400 seconds. And that seems to be some sort of law of nature, right? That there's no combustible source that will produce ISP of greater than 400 seconds or so. And you can see no matter all our technology over time has not produced propellants that can significantly exceed that. Burning propellants, that is. Now there's an exception, of course, for electric propulsion, where we can add energy to the propellant through electricity, and then we can get away from these limitations on ISP. But that does require electricity. Right, and so in these cases, right, all of these propellants have the energy self-contained. Energy in the propellant itself. Don't need to add anything. And for these electric rockets, requires solar panels or some other way of creating electricity. Obviously, we could never, in first stage, create enough electricity or energy to get a rocket off the surface of the Earth. These first stages will always need to be self-contained, so we're limited really with these first stages to these ISPs that we see here. And again, this is why Hohmann was so excited. If you ever bothered to read his manuscript, which is very nice, he was very excited by very small improvements in the ability of propellants to produce larger ISPs, because that translates directly into delta V. Unfortunately, we haven't ultimately improved those numbers very much, even since the time of Hohmann. Right. Again, the effective ISP depends on your rocket nozzle and so on and so forth. And so the numbers listed in all these tables are sort of the ideal cases, and assume a perfectly expanded rocket. So not to be, again, taken at face value, especially for that first stage, so the ISPs for the first stage are typically a little bit lower than the upper stages. All right, so at this point we can do a few quick calculations, right? The numerical problem we had at the beginning. We want to lift a 30 kilogram rocket into space. Our ISP is pretty much limited to 300 seconds because that seems to be some kind of law of nature. And the question is, how much propellant do we need in order to achieve a parking orbit, basically? Right. So if we learned earlier on that circular orbit at 200 kilometers has a circular velocity of 7.7 kilometers per second. To that, we need to add some additional tolerance, again, to account for that initial time when we are burning perpendicular to the gravity or parallel to the gravity, right? That's wasted, right? And that's that. So we need to add basically 1.72 kilometers per second of delta V, which is wasted fighting gravity, and then there's also some delta V, which is wasted fighting drag. Right. So this is also why these sky launched, the Pegasus rocket, for example, launched off a plane, is very useful. Right? Here's a plane. That's my plane. I know it doesn't look like a plane. So as a rocket attached to it, you drop the rocket and then it burns off. It doesn't have to fight gravity. You use the plane to get it above, and so you can save some of this 1.2 kilometers per second if you use a plane-launched rocket. But again, it's sort of a law of nature. You can't get lower than 7.72. Now you can use the rotation of the Earth to get you about 0.5 kilometer per second, but not more than that. And then so generally a rule of thumb, I mean, it's not a hard and fast rule, but a rule of thumb is that your delta V to get into space, to get into a circular parking orbit, is going to require a delta V of at least 9.5 kilometers per second. So if we have an ISP of 300 seconds, how much propellant do we need, basically? Through 300 seconds, ISP 300 seconds means exit velocity of 3 kilometers per second. Plug these numbers into the rocket equation, right? That goes there. The number goes there. The delta V we need, where's that delta V? That number goes there. Right? And so we have these two numbers. We have, that's just the exponential number. E to the, we just calculate this number. We find that the mass of propellant to the mass, total mass of the rocket has to be 96%. Right? So the propellant has to be 96% of the total mass of the rocket, right? So the total mass, of course, is, remember, the propellant mass plus the structural mass plus the payload mass, right? So the propellant itself, right, has to be 97% of all three of those things, right? So these things have to be relatively small. In our case, we fixed the payload mass at 30 kilograms. We're going to ignore the structural mass here, right? And so the wet weight is just the payload mass plus the propellant mass. And so even with that very conservative approximation, we find that the propellant weight has to be 682 kilograms to lift a payload weight of 30 kilograms, right? And so we see even with no structural mass at all, we need a great deal of propellant in order to produce even a very small amount of payload, to lift even a small amount of payload. And that doesn't account for structural masses. And of course, once we get up there, right, there's no delta V budget whatsoever. We can't go to Mars or whatever we have to deal with later. We'll come back to this issue. It's quite serious in just a minute. First, we're going to take a small detour and talk about the various types of rockets that are used, and so the advantages and disadvantages of each, and when they're used. Right? So, and we'll start with the most basic rockets. It's solid rockets. So if you use, if you have model rockets, for example, they all use solid rockets. Fireworks, right? You are basically solid rockets. Right. And the solid rocket concept is really quite simple, right? You have something like gunpowder, right, in here. Right, you've got this this casing, right? You've got the solid rocket casing. The gunpowder is packed onto the solid rocket, onto the casing, right? Leaving this this area here exposed to the air. Well, not the air, of course, but just exposed. And they're designed in a very specific way, so that as you burn through this propellant, it burns evenly, so that it burns out a little bit there, burns out a little bit here, and so as it burns out, the packed propellant gets thinner and thinner until it gets actually to the shell of the rocket, at which point the rocket burns out. And ideally, you would like all the propellant to burn up, to burn out simultaneously. So you don't want a little pocket of propellant here still burning when everything else, because it's just going to be wasted. Once the propellant burns out, the rocket is useless. So you separate that. You dump the rocket. You dump the stage. The mechanism is very simple. You create a spark. It's just like a gun, right? You create a spark here. It ignites the propellant, the gunpowder, if you will, which burns, creates a very high combustion chamber temperature, right? Which spits out the back of the rocket into the exit cone, right? Because it's like a gun, however, it's almost uncontrollable, right? Once you light a solid rocket, there's no way to turn it off, right? Not adjustable. So that rocket is going to burn until it, well, burns out or explodes or whatever, right? So that's a very strong disadvantage. You never use these things except in the case of brute force, right? To get off the launch pad. If you're going to need to maybe make fine adjustments to throttle your thrust or whatever, you don't use solid rockets, right? Another disadvantage of the solid rockets is, of course, the performance. As we see, the ISPs tend to be a little bit lower, and that's partly a result of the composition of solid propellants. Like they typically contain heavy metals, and metals being heavy, right, limit the efficiency, right? So there's a temperature of the combustion, and the temperature sort of divided by the temperature is proportional to the exit velocity, but the weight of the propellant, the mass of the particles of propellant, is inversely proportional to the exit velocity. So that implies that brings down the exit velocity, because that temperature can't accelerate those particles fast enough. So you have heavy metal propellant fuels, and they also tend to be, because they're heavy metals, tends to be toxic. And so if you like crash wood on dry land or Kapustin Yar or whatever, right, you're going to have like cabbages growing up which are not entirely healthy, right? Kapustin Yar, of course, meaning cabbage field in Kazakh or Russian or something like that. And then that's we get these toxic byproducts that we're talking about here. The advantages, of course, is it's relatively simple. We've been using them for hundreds of years, right? Ever since fireworks and rockets were created. They tend to be actually reliable. They don't tend to explode. There's not many moving parts. And so solid rockets tend not to explode. So that's generally a good thing. They don't leak, right? There's no sources of leaks like we do have in liquid rockets. And they tend to be a little bit cheap, right? Again, partially because there's not as much attention devoted to safety. That's one reason that they tend to be lower cost. Here's just a list of solid rockets as of, I think this is like 10, 15 years ago. These are the IUS and STAR correspond to the company making them. That was Thiokol, Morton Thiokol back in the day. Now ATK Launch Systems, I believe. IUS is United Technologies, which is of course still in existence. And so these are the rocket manufacturers. You just buy them sort of off the shelf. They have lots of variations you can see here. This various STAR rockets and the various IUS rockets. Well, I actually only see two here. Let's see, what can we point out here? The specific impulses are all about the same, between 280 and 300 typically. So that's just because propellants, right? You can't do much better than that. The numbers here are mostly indicated by the size of the rocket itself, so the loaded weight, right? Bigger rockets, smaller rockets, right? Producing larger thrusts, smaller thrusts, right? And that influences, of course, right? That's mostly a factor of how big the rockets are, the propellant mass fraction. So how much propellant we have to structural mass. So these are low because they're not big rockets. There's economy of scales for large volumes that we get. So these are small volumes, so they have relatively little propellant to structure ratio. And these are larger ones, so they have relatively larger, more propellant per unit structure. Right. These are, again, producing really high thrusts. These are producing low thrusts. Next on our list of rockets to go over is the liquid monopropellants. So there are liquid monopropellants and liquid bipropellants. The monopropellants are simpler to some extent, safer, fewer moving parts, less explosive. Liquid monopropellants actually work through catalytic decomposition, right? So basically, you have the liquid propellant here. These tend to be hydrazine rocket type things. Let's see, yeah, here's hydrazine, right? And they don't naturally explode on their own, but they are vulnerable to catalytic conversion. So they move through here into a catalytic converter here. I guess not quite what's on your car, which allows these complex molecules to decompose into smaller molecules, right? Decompose N2H4 to NH3 and nitrogen and hydrogen. Okay. This is still nasty, right? This I forget what that is, but simpler molecules still not entirely pleasant. But they go through the catalysis that produces rather large temperatures, 1800, 2000 degrees Fahrenheit, which then, of course, are expanded in normal ways. The catalytic conversion is there's some energy contained in this decomposition, and that's released as in form of these temperatures. Not quite as efficient as bipropellants, though. Bipropellants are taking smaller molecules and forming larger ones. These are taking larger molecules and forming smaller ones. And that tends to be a lower energy process. However, they're relatively simple, right? They're reliable. They tend to not to explode because you really need this catalysis to cause the temperature, the decomposition. And due to the simplicity and reliability, they're typically rather low cost. These are often used for maneuvering thrusters or attitude control thrusters up in space. They tend to not be used for large rockets, right? These are small rockets. Right? They're not used for large delta V changes. That's partly because they have smaller specific impulses, smaller specific impulses, and that the catalysis it can't really be scaled up too much. By contrast, if you really want large delta V's and high performance, you typically go with the liquid bipropellants. Performance. Switch to delta. Actually, maybe I'll switch to there. Right. So in this case, this is what we know. We've seen it many times. This is an upper stage actually to the Centaur. So this is what's like used to lift a GEO, for example. So this is like once you're already in space, or if you're going to Mars or whatever, you would use these upper stages. It's also it was used in the space shuttle main tank. And more recently, I believe the BFR, for example, I believe is entirely liquid propellant. Or whatever, the Starliner as it's now called. Right, so how do liquid bipropellants work? Right, so let's see, where's my cursor there? It's hard to see this one. So liquid bipropellants, of course, work by combining lighter molecules, hydrogen, oxygen, into, they combine them, they burn essentially. Hydrogen burns with its oxidizer, which is oxygen, and they produce essentially water. Yeah. So you can catalyze, you can electrolyze water and produce oxygen and hydrogen, and then recombine them for rocket fuel. That's why it's so important to be able to find water on various planets. Right. So there's some complexity to this process which isn't present in any of the previous rockets we have. So specifically, these two propellants have to be combined in a fixed ratio, right? And that has to work dynamically. So you see here, there's this gear assembly which links the rate of the flow rate of these rockets together. There can't be any leaks. That's very important because oxygen will burn up anything it comes in contact with. And as will hydrogen, of course, if it encounters air, for example. So can't be any leaks. Can't be this ratio has to be fixed. And of course, hydrogen requires very low temperatures, right? Liquid hydrogen and liquid oxygen, to a lesser extent, requires very low temperatures, right? Very highly cooled tanks. In this design, for example, that's actually used. So we have liquid hydrogen here, very cold. It goes through this. Let's see, if we can get this. Maybe I'll move to that. It goes here through this pipe, right, which is all fine. And actually, it's so low temperature, it's actually used as a coolant to prevent the nozzle from burning. And then it heats up the propellant a little bit. And so, which is okay because then it gets combined here with the oxygen, and in the expansion chamber, it produces a high temperature. Right. The liquid oxygen is not used for cooling because it's not quite such a cool temperature. Also, this pressure is once it's heated up a little bit, used to spin this turbine here. So. Advantages, of course, is that this reaction is very exothermic, produces very high temperatures. You can get, for this hydrogen-oxygen reaction, you can get ISPs of 400 seconds, up to 440 seconds. The disadvantages, of course, is this: when you see rockets explode, it's almost always because of the liquid propellant case. Oops. Right. Complicated, dangerous. Now, obviously, producing water is not toxic, but there are other liquid bipropellants which are toxic, and so sometimes toxic. Advantages, of course, you can turn it off, right? That just rotate your gears, close the nozzle, turn it off, and high performance. So, but again, there's a leak. These gears don't work precisely as designed, and you have an explosion and you lose the rocket. Okay, so here we go on our table, right? List all of our rocket types that we've gone through so far, and some we haven't. We'll get to these in just a second. So cold gas, low ISP, solid rockets, reasonable ISP, but a little bit lower than the bipropellants. The ideal case here being hydrogen and oxygen, which have a very high ISP indeed. Both of these cases, the bipropellants and the solid rockets, can produce very high thrust. The monopropellants, however, very low thrust, right? They're limited by that catalytic converter. The density, right, and this is going to influence structural mass, right? This density, especially for hydrogen, is going to contribute to structural mass, and so you have to pay attention to that. 1.14, solid rockets 1.8. Cold gas, right, the density is very low. You want this number to be high. High is good. But of course, the 0.7 here is bad, right? So sometimes we use sometimes we use very toxic components such as fluorine. Nothing gets more toxic than fluorine gas. Really, very little can stand up to fluorine gas, fluorine and hydrazine. Let's see. We also list here, which we're going to talk about in a second, hybrid rockets, which sort of combines some aspects of the solid with the aspects of the liquid, but in a less complicated way, which you don't need the gears and stuff for. You still have leaks, but you don't need the gears. There aren't as many moving parts. In addition, we'll talk a little bit about these electricity-based rockets, the electrothermal, electrostatic, and electrodynamic. Right. So we'll cover very briefly hybrid rockets here, right? So in this case, we have the liquid part, which is a storage tank for your oxidizer, right? Of course, that leaks out. Anything comes in contact with will burn. Not quite as bad as hydrogen, because if it leaks out, oxygen and oxygen don't mix as much, but hydrogen and oxygen do, but still dangerous. So you have to watch out for leaks. It's the oxidizer passes by what is essentially a tire, rubber, or paraffin, which rubber or paraffin, if they come in contact with liquid oxygen, burns very hot. But again, this is packed, right? Right, as solid rockets typically are, and so packed in such a way that it needs to be packed in such a way that it sort of burns out evenly. It produces high temperatures, which then goes out through the nozzle. Disadvantages and advantages. Basically, disadvantages are all in the liquid part. Right. Requires oxidizer, right, which is dangerous, which can leak. Bulky oxidizer tanks. It's not quite as bulky as hydrogen, so because these are relatively dense, so that's good. So it's not that bulky. Advantages then being it's throttled, and that solid packing just generally prevents moving parts, makes things a little bit more reliable. It's been flown various spaces, famously on Spaceship One. In that case, the oxidizer was laughing gas, nitrous oxide, not quite as dangerous as liquid oxygen. Produces a relatively low ISP of 250 seconds, but again, not significantly lower than most solid rockets. But again, the advantage here being it can be throttled and turned off. So we just some examples of hybrid rockets which have flown. So the American Rocket Company produces quite a few of these. Relatively high thrusts, not too bad. I believe HTPB is paraffin. United Technologies has its own. There's an experimental one here. More experimental ones. Again, right, this is a relatively well-developed technology. It's a little bit newer, not quite as common as the others, but still in use. Often from plane launched rockets, it's more reliable, doesn't blow up your plane, and that kind of thing. Yeah. Okay. Lastly, last rocket type that we're going to consider is the electric propulsion case. And again, I want to emphasize throughout that the electric propulsion, they have high ISPs. However, the cost is, but need electricity. And so unless you have a nuclear rocket, you're never going to produce huge amounts of thrust with electric propulsion unless you have like a nuclear power plant on board your rocket. And in fact, you actually need a nuclear power plant for this particular type of electric propulsion here. All right, so they're generally organized into three categories: the electrothermal, so that's basically resistance, heating. You pass current through a resistor. It produces heat, get high temperatures, it spits out the back of the rocket. Electrostatic, so you produce charges or use a capacitor to produce charge differences between plates, for example. Ion engines, for example, electrostatic. That difference, that charge difference, that electric potential accelerates charged particles and accelerates, in this case, out the back of the rocket. Electromagnetic, there are various variations on this, which we'll talk about in a bit. You ionize basically the propellant, and then you use magnetic fields to accelerate those charged particles. So again, we'll talk a little bit about this in a second. The advantages of electric propulsion is very high performance. Disadvantage mainly being it requires electricity. Of course, the more electricity you have, the higher the thrust. But if you want high thrust rockets, you need boatloads of electricity to make that work. So typically, what you have is you have a solar panel attached to the spacecraft. It produces electricity. That's used to accelerate your propellant out the back, right? But not very fast. So it's usually for station keeping, Hall effect thrusters, that kind of thing. Typically used for station keeping or continuous thrust trajectories. Now, continuous thrust rockets trajectories in space are not terribly common, getting more common. Processing economy has a whole chapter devoted to them. The mathematics are quite complicated, so I'm not going to talk about them too much. I will talk about like these two particular cases here. Let's see. Here we go. Push that. So this is an electromagnetic case, right? So that's that one. This is an electrostatic case, right? I think it's on the next slide. The precise ones. This is the gridded ion thruster here. That's the one on the right. The magneto-hydroplasma dynamic thruster is the one on the left, MPD. In this case, as far as I can remember, where's my pointer? There we go. You spit these charged particles out the back. You have these grids here, these charged plates, and they're charged here. You have positive grid and a negative grid. So the particles move through the plates. They move away from the positive plate towards the negative plate, come out the back, neutralized by these electrons, which are spit out here, so they don't come back and bump into you again. And this potential, electric potential, right, is what accelerates the propellant out the back. Now, the propellant itself is not exothermic in any way. It's not explosive. It's neutral. All of these electropropulsion have neutral propellants, not exothermal, right? And as a result, they tend to not explode. They can be used for long periods of time without any danger. Again, assuming that you have unlimited electricity. These are relatively old designs. This is, remember, from the 1960s. Right? The gridded ion thruster. The GIT. MPDs have never flown, basically. Magnetoplasma dynamic thrusters. It's essentially like a tokamak nuclear reactor. You use magnetic fields to confine the plasma. Let's switch to red here. So use magnetic fields. Let's see, where does it say? Superconductor generates magnetic fields, right? That's the magnetic field. The magnetic field is the current runs like that, right? Which, if you have a charged particle, that means that if your motion is in that way, it'll bend it back that way. And so these charged particles that you have in the middle here tend to cycle, right? They produce little spirals here, helical structures, which means they don't escape and bump into the side of the chamber. Right? Meanwhile, your use radio frequency resonant heaters, right? So you generate radio frequency waves at a specific frequency that interacts with the particles, and that heats them up, vibrates them essentially. They don't. They get very hot, right? Millions of degrees. See here, million degrees. They heat up by these ion cyclotron heaters, radio frequency generators. Get very hot, but they're confined. They don't. The thing doesn't explode at 1,000,000 degrees. Very little survives 1,000,000 degrees. But they don't explode because they're confined by the superconducting magnets. They've been ionized here, right? That's what allows them to be confined, and so they get heated up to 1,000,000 degrees, and then just the temperature of that, when you release it out the back, produces a great deal of thrust. So this is the MPD design, magnetoplasma dynamic, and it has ISP greater than 4,000. Very high ISP. At the cost of course, requiring a great deal of electricity to produce these magnetic fields, very strong magnetic fields, and especially to power these radio frequency heaters. So I had the gridded iron thruster here. That's what the U.S. developed in the 60s. Soviet Union worked on the Hall effect thrusters. It's essentially slightly different, but essentially do the same thing. They're all used for station keeping. They don't produce great deals of thrust, but they do it very efficiently. So once you're up there, you can produce lots of delta V. You just have to spread it out over very long times. And these MPDs, again, only experimental. Haven't really because essentially they require a nuclear reactor to provide the power that's necessary. Solar panels, not enough. All right. So electric propulsion, again, broken down electrothermal, just resistance heating. Provides very little, it actually doesn't provide that much ISP, but only doesn't require that much heating either. I mean, as you might expect. By contrast, electrostatic requires more electricity and produces more ISP, more C, more faster cannonballs. And the most efficient electromagnetic, if you're looking for high delta V for delta V over massive repellent, electromagnetic's your choice. But again, it requires very large electrical burdens. The pulse plasma is probably on the low end, and the MPDs are on the high end. Look at that 1 megawatt power. You can never build a solar panel big enough to provide 1 megawatt of power. You essentially need a nuclear reactor to provide that much power. So let's see what we got here. PPTs, right? By contrast, right? Salt River Project Power is a power company, local power company, and provides power for a portion of the Phoenix metro area. In its entire average power generation is only 3.2 megawatts. So a medium-sized city, enough power for a medium-sized city is required to run those MPDs. PPDs, again, the final sort of class of thrusters I want to mention, right? Relatively old pulse plasma thrusters. So basically, you charge up a capacitor, right? You have your Teflon block here. You spark it to create plasma. That's ionized particles. So you get positively charged and negatively charged particles. That capacitor is discharged, right? Creates a very high current in this direction. If you know, the current generates a magnetic field in that direction. Magnetic field direction acting on a charged particle will tend to push it out the back. So it creates this this law through the right-hand rule, which creates force on the particles in this direction. Only for a very limited amount of time, of course, because then you have to recharge the particle and push more thrusters. So it's generally very low thrust, but can achieve relatively high specific impulses. 70 watt, not great power requirements, so it's relatively minor. So this is the most recent NASA research PPT, ISP of 1300, which is pretty good. Right, so to summarize our electro propulsion ranges, we got the resistojets here. That's just ohmic heating, not generating great ISPs, but again, the propellant isn't going to explode on you, so that's good. Arc jets, similar to that, you just create it's not resistance, but it's you create an electrical discharge. You get higher ISPs, heat it up a little bit, heat up the propellant a little bit more. PPTs, right? You can get higher ISPs, but they tend to start requiring lots of power. Where's the input power? Right? Well, actually, these PPTs don't require a lot. The Hall effect thrusters and the ion thrusters, so there's a Soviet version, this is the American version, generate these higher specific impulses, but of course require a great deal of power. So what you're really looking for is the thrust to power ratio, so the amount of thrust produces per power. So Hall effect thrusters are slightly better at that metric than ion thrusters. But generally operate at higher power requirements. They all use these neutral elements. They're never going to explode. They're very stable. I mean, this is an inert gas, basically. So these are very safe propellant. They're usually used for station keeping and not much else. Not used for high delta V maneuvers. Although continuous thrust is now becoming more of an option. Again, they're powered by Teflon. Melts at 327. If you wonder, nothing ever sticks to Teflon, but Teflon sticks to the pan. That's because at 327 and between 327 and 400, Teflon does melt and then it binds. But of course, when we're talking about PPTs, we're talking about much higher temperatures, and then you want your Teflon, in fact, to ionize from a plasma. All right, so how are we? We're running a little bit late, but I'm just going to push on through here. If you're watching at home, you might want to take a break. Because we have one more subject to talk about before we wrap up for the evening, and that's staging. Staging is, I said, when you pile rockets upon rockets. Right? Just take off my sweater here, get a bit warm. So let's see. Here we go. Let's draw a little picture. Let's consider, for example, the limitations of a single stage rocket. So we had a rocket diagram here, which we had a payload. Actually, I'm going to call it MD in my eraser. Go, MD. We have a structural mass here, right? And that structural mass is what's used to contain this this propellant mass here. So this is the fuel. This is like the rocket nozzle, the fairing, that kind of thing. The thing that you use to contain the propellant. And this is what sits on top of the rocket. So we have a single stage rocket here. Previously, we assumed that the rocket only consisted of payload and propellant. So we ignored this bit here, used to contain the propellant, and then the nozzles and stuff used to like spit it out the back. So in this part of the lecture, the last 7 slides, we're going to be talking about reality, right? Reality. The reality is that we need structure to contain the payload. Rockets are not popsicles, right? They don't just burn off the top, the bottom, and use up the structure as they go. They have tanks and they have nozzles, and those have weight, right? And specifically, we have sort of fundamental laws of nature, which say that there are limitations. We can only reduce the structure so much before our rocket becomes unsafe. We can only reduce the structure so much before, while still maintaining our nozzles and our tanks, right? So that they don't leak, they don't explode, that kind of thing. And those numbers have not changed a great amount over time. Of course, the bigger you build your rocket, it tends to be the economy of scale. You can get lower structural percentages. But that number really doesn't vary too much from 1/7 to say 1/10 of the propellant mass has to be devoted to structure, right? The storage tanks, the nozzles, right? And those things are heavy, and that's why propellant can really never be more than 6/7 of that part of the rocket itself. And then, of course, we have to add the payload to that as well, right? So that rule about 1/7, we talked about structural mass fraction. We'll talk about that more in a slide coming up. But that structural mass fraction 1/7 poses fairly severe limitations on what we can achieve in terms of delta V. So if we look at the rocket equation, here's the rocket equation here. Right? We have to add to the rocket equation now plus 1/7 MP. Plus 1/7 MP. So that even in the most ideal case, so even if we have 0 payload, right, we are still going to have this structural mass, which is 1/7 MP. Right? And so if we look at the limitations of what delta V's are possible, so we make MP and payload 0, right? On the top we have MP, and on the bottom we have MP over 7, right? Right. If we just crunch those numbers, right, the MPs cancel, and we just get CLN 7, right? So if we have no payload at all, then the total delta V of the rocket is going to be limited to, and here of course we've neglected the structural mass up here. But the total delta V, if we just calculate what natural log of 7 is, right, the total delta V of the rocket is going to be limited to 2C, whatever C is, and assuming that C is something reasonable, say 3 kilometers per second, ISP equals 300 seconds, then the total delta V of the rocket is going to be limited to 6 kilometers per second. And these are rough and ready calculations, but you may notice that 6 kilometers per second is significantly less than what we need, which is 9.8 kilometers per second in order to get out of orbit. Right? And that's even assuming we have no payload. Right? By contrast, right, the delta V required for low Earth orbit, minimum parking orbit, is 8 kilometers per second and possibly 10, right? And we quickly realize that a single stage rocket cannot establish a parking orbit, right? So single-stage rockets cannot establish a parking. And this was what was so concerning to Hohmann when he was talking about getting into orbit. People were concerned whether it would ever be possible to launch rockets into space because of this fundamental limitation. So they were really hoping that the C would increase, right? And of course, it never did substantially. And so, of course, you could take the slide and conclude that spaceflight is impossible, which of course many people did, and that it's all a giant conspiracy, and the moon landing was staged in Arizona somewhere. No, actually, the moon landing was staged in Mexico, I think. Yeah, it was not. It was not, of course, really staged. But if they wanted to stage it, they could stage it in Mexico. And so the question is then, right? We know, hopefully, that spaceflight is possible, and so the question is why. And the answer, of course, is staging. Right? The answer is that we want to use up. We don't want to include this structural mass in the payload mass. And so how do we avoid doing that? So here we just have a cute little illustration of the structural mass of the Saturn V rocket. So this is the inside of the Saturn V rocket, Saturn V rocket, between stages. So you hear and see there's this first stage dropping off, and we see here, it looks heavy. Basically, it's a lot of structural mass. It's a very big rocket, of course. So volume to surface area ratio being high. It's not as bad a structural mass fraction as some rockets we have nowadays. And then, of course, we see here the adapter, which is about to pop off, hopefully. Adapter. Any day now. That adapter should pop off at some point. I'm just going to accelerate the process here. Oops. There it goes. Sorry. Okay. Yeah. So then the adapter is what holds the first stage to the second stage, and you can see it's relatively substantial, weighs a lot. And then, of course, we have a whole set of new nozzles for the second stage, which is all payload on the first stage. Right? So a lot of weight here, which we have to account for. You see it floating off into space, going back to Earth. It's going to re-enter. I'm going to light up these rockets at some point. No, I guess we're just going to repeat. Right. So let's see. All right. So that's structural mass. Structural mass is as I said, relatively large. Here we've got one that I actually play by itself. This is a Soyuz rocket launching European Space Agency satellite. Just accelerate here. There's Ariane space, upper stage, the fairing being rather large here. So the fairing itself, of course, is rather heavy, and all these the structural mass is rather heavy. And the only thing that's actually going up into space is inside of this fairing. Are we going to launch here at some point? Yeah, there we go. So there we go. It's a Soyuz rocket. It's got these solid rocket boosters here on the side. It's going to eject those at some point, going up into space. See, again, nicely expanded rockets here. It should be less expanded as time goes on. Getting a little underexpanded. Getting a little chaotic motion there in the rockets. And the expanding, the atmospheric pressure decreasing, rockets getting less efficient. And here that's the first stage. At some point in the near future, we're gonna dump those. We're getting up very high. We're only at 57 seconds. We're doing our roll, so we're gonna go trying to move sideways at some point here. And so we're turning the rocket a little bit. See the nozzle, those solid rockets burning out there, getting overexpanded. We've made our turn here in less than 1 minute. So we're no longer fighting gravity here. And there we lose that structural mass from the solid rockets there. I think pretty sure those are solid rockets, as far as I remember. And then we're gonna separate here. We've got our second stage. We're gonna get the fairing separation here. We're now at about 212 seconds. We're in space. There's that upper casing to the rocket, which is just left. We're going to get a second stage or third stage here. Shortly, hopefully. Yeah, so second stage plus Soyuz third stage, rear section separation. So, boom. There goes the previous stage. There's still the adapter here, I believe. Yep, there it goes. The adapter, again, all extra structural weight, and the new nozzles that are being used, again, structural weight. You can see here, I believe, the third stage and bay separation. Right, so there goes the stage, pushing itself back to Earth. And here we're releasing the satellite. And the whole upper stage, of course, they're becoming structural mass for our tiny little payload here. Right. So again, far more structural mass is being ejected here than actual payload. All right, so this nice little interlude, courtesy of the ESA. So now we'll talk a little bit about these structural masses. So the the physical limitation of the system. The physical limitation is this structural coefficient. This is sort of the base per, no matter how much, how big are each of our stages, it sort of gives the amount of structural weight required for a given amount of propellant weight. So you can solve this equation for propellant weight for structural weight for a given amount of propellant, right? And this is sort of a law of the universe. It's not a design factor at all. It's sort of like just what the limitations on materials are, and it tends to be in the range of 1/7 to 1/10, depending on the size of the rocket, right? So ideally, if you had an infinitely staged rocket, right? That's the ideal, right? We have a rocket like this, right? And our structural weight is only tanks, right? So in the ideal case, we have an infinite number of tanks, right? And each of those tanks has a little bit of structural weight determined by the structural mass fraction. And as soon as we use up that delta, sorry, I should be using my pen. As soon as we use up the delta MP, we also use up the delta MS, right? So that in the ideal case, right, if we, for every bit of propellant, if we used up the accompanying structural mass, burnt it out, we would have the case of ideal continuous staging. Right? This is the ideal case. So like a popsicle rocket, right, where there's just like this thin film on the outside, and it's burnt up as the propellant is burnt up as well. In that case, in fact, the delta V, the rocket equation, doesn't change substantially. So in this case, the efficiency of the specific impulse of the exhaust velocity is just reduced by a factor of 1 minus epsilon, which is typically, you remember, about a seventh. So it would just, in this ideal case, it's basically just, this is a dead propellant which isn't used. It just reduces the effectiveness of the propellant. So this is the ideal case. Of course, it never happens, but this is what we're looking for. Because in this case, we find that any delta V is again possible, right? We don't have to account for the structural weight because it's used up continuously. And so that structure just adds unenergetic parts to the propellant. Right? So it just reduces the efficiency of the propellant, decreases the efficiency of the propellant. Of course, that's not what actually happens in rockets, but it tells us that efficient use of staging can basically be used to achieve any delta V. So again, we come back to this question. It's not a matter of a space flight is impossible. It's really a question of how many stages we can put on our rocket, or how many stages we need, and how much propellant, how big a rocket we need to achieve a given delta V. So again, so this tells us the ideal case, ideal scenario, staging will allow us to once again achieve any delta V. So this also gives us sort of an upper bound on how efficient our staging can be. So if we had infinite number of stages, our delta V could never exceed this limit, right? But of course, typically we don't have infinite staging, and nozzles take up a particular part of that staging. We can't have infinite nozzles. So this doesn't account for like nozzles and adapters and stuff, which are typically fairly fixed weights. So we don't have that. A couple terminologies, right, that are used in processing. We're almost to the end here. There's there's the structural weight, which is on the previous slide. Epsilon equals m. So the ms plus mp. So this is the structural coefficient. Structural coefficient. That's the jargon they use for that, which indicates the mass of structure for the total mass of the stage. So it gives for a given stage, how much of that stage is going to end up being structure. Right. The next number we look at is mass ratio, which refers to the full weight of the stage over the empty weight. Now this is a different number because if you look at our rocket here, right, here's our stage. So say it's like it's one of these rockets. It's a two-stage rocket, right? There's a rocket on top of a rocket, basically. There's a nozzle there. There's a nozzle there, right? This refers to something slightly different because now it includes the payload, right? This is more of a design parameter, right? So for a two-stage rocket, for example, the Z of the first stage refers to the propellant and mass of the first stage, plus all these stages that go on top of it. Now Z's are relatively kept relatively constant, and they're dictated by you can just solve them explicitly in terms of another number which is called the payload ratio. So there's a mass ratio of total weight of this, everything divided by just the weight of that stage, right? Stage stuff. And that's determined uniquely by, of course, this number, which is a law of nature, doesn't change, and this payload ratio. And the payload ratio indicates the ratio of payload to structural mass plus propellant. And so this is more the design parameter I think that people tend to use, which is the ratio of what's above that stage to the stage itself, right? So this to this, right? That ratio, and that's important, right? This lambda, because you usually keep it a relatively constant, right? And what that means is that the size of the stages will tend to decrease over time because the size of what they're lifting decreases over time. Size of stages decreases as we get to further stages. So first stage is bigger than second stage is bigger than third stage, right? The size of stages decreases if, of course, lambda is a constant, right? This is, again, a design parameter, something you choose. We find that it's somewhat optimal to choose a particular constant payload ratio. Again, it's a parameter which can be optimized, and I think there's a homework problem where we're looking for optimal payload ratios. And finally, I just returned to this, what I refer to as a structural mass fraction. I sometimes use this expression on the exam, so I want you to know what it means. It's different than the structural coefficient because it's just the mass of structure divided by the mass of propellant for a given stage. So it's the amount of structure you need for a given amount of propellant. The mass of structure is a constant fraction over the mass of propellant, which is essentially the same thing as structural coefficient. You can definitely get it from structural coefficient. It's just the structural coefficient is the mass of the stage divided by the mass of the structure, and I just think of it like as how much container is needed for a given amount of propellant. But that doesn't include the nozzle, so maybe that's not a good term to use. By far, structural coefficient is more common. Okay. So, given all this, right, that more or less gets us to where we need to be. We can calculate the delta V, right? We can use the rocket equation for a multi-stage rocket just by taking the rocket equation for each stage, right? So this is MF, right? And this is M naught. Let's call it M naught 1 and MF1, right? And remember the rocket equation is M naught divided by M naught 1 divided by MF1. So the final mass is everything that the rocket lifts, including its own structural weight, right, which goes in there, right, and then of course all the stages that come above it, right. And then the only difference between the top and the bottom is the top is wet weight and includes the propellant for the first stage as well. And then so that's the delta V you get off the first stage, and then the delta V you get off the second stage is essentially the same thing, right? We've jettisoned the structural weight, and so the delta V from the second stage is, right, yeah, I need to get better at this, M naught 2, and then MF2. Sorry, you can't really tell that. There you go, MF2. And then so you get a delta V off that. That's M naught 2. This is MF2. And then the delta V you get from the third stage, for this three-stage rocket, obviously, is again, maybe I need a new color here. once we've jettisoned that second stage structural mass, right? That's m naught 3. Use a different color here, maybe black. And sorry, no, just erase that. That's m f 3. Right. So this payload includes structural weight in that, if we like, ms3. The initial weight of the third stage is propellant plus payload, and then the final mass is just payload. And so to get the total delta V, we just add up the delta V's accumulated by each of the stages, add them together, and that gives us the total delta V. Now we have lots of design parameters here we can think of. Well, typically the payload is fixed, so we can't really play around with that. The structural mass is typically, right, that structural mass fraction, like the one I talked about on the previous slide. So we typically let that be 1/7 mass of the payload or something like that. Again, that's my 1/7 structural mass fraction, and that's why I use this term a little bit, because it just, right, you don't have to convert it to epsilon. You can find it as, remember, it's epsilon or 1 plus epsilon, I think, from the previous line. Yeah. And 1 minus epsilon is fine. Right. Right. So the structural mass is fixed by your structural coefficient, which again is sort of a law of nature. And so here we get what we have to play with, right? Then the only thing we have to play with really is MP, M1, MP1, MP2, and MP3. So we can choose those 3 numbers. Right? Those are design parameters. In a single stage rocket, we'd only have 1 to play with, but here we have 3. So there's 3 variables. So these are So given, we typically choose these variables, we pick them to optimize something, right? All of life is an optimization problem. So we're choosing these variables to optimize something. So one scenario, the one I'll show on the next slide, is we have a fixed wet weight, right? A fixed weight that the whole rocket has to satisfy, right? Right. A fixed weight, and then we, given that fixed weight, we can either optimize the payload for a given delta V, or we can optimize the total delta V for a given payload. Right. Okay. If we're not really into optimization, although certainly in real life we would be, a good simple rule to give a relatively constant payload ratio is the propellant mass of the first stage is 3 times the propellant mass of the second stage is 3 times the propellant mass of the third stage. Just, not that great a rule, but just to give you some intuition, that's how it typically shakes out. So here's some data, right, on various rockets, for example, giving real structural ratios. Structural coefficient of the Saturn V, this is like that really old rocket from the 60s. Structural coefficient first stage 0.06, which is good. Structural stage of the second. Structural coefficient of the second stage, 0.08. Structural coefficient of the third stage, 0.09. And you can see it's decreasing, and that's because of the size. The bigger the stage, like the more volume the higher the volume to surface ratio, the less those propellant tanks weigh. And that's why you're getting that really big first stage leading to a good structural coefficient, and the later stages not so good. And you notice also this hasn't changed much. Like in 1988, the Ariane 4 structural ratio is still 0.07, even worse than the Saturn V, and that's mostly because it's a smaller rocket, right? It's a smaller rocket. This is, I believe, the total weight of the rocket here is given somewhere, maybe. Well, it's an interstage. Well, I guess I don't see it's given here anywhere. Oh, wait. That's the third stage. Oh, there it is. All right. Yeah, so the total weight of the Saturn V is 5 million pounds, and the mass of the Ariane 4 is between 5 and 1 million pounds. So it's just a bigger rocket, and that's why you get a slightly better structural coefficient. Also, I just threw out the BFR, right? It doesn't go, is actually, again, still worse. All now named the Starliner, of course, is actually worse than the Saturn V. I think that's because is it made of steel or something like that, but it's made of something. So it achieves a worse structural coefficient despite being bigger than the Saturn V at 11 million pounds. It's also a two-stage rocket, notice, as well. Just, I guess, to improve some recoverability, reusability, something like that. So that's modern rockets. Again, these are sort of laws of nature. Go along with ISP, they don't change a whole lot with time and technology. So finally, we get to some numbers. This is a table from Pressing and Conway, which has a total fixed weight of the rocket in all of these cases, right? And it considers a 1, 2, and 3-stage rocket. In the 3-stage case, it considers the case of for a given total weight, your given payload. You're maximizing. Your given delta V. You're maximizing payload lifted, and so that given delta V is right there. And for a given payload, you're maximizing delta V. And that given delta V is right there. So here your payload is 1,000. That's your specified. Here your specified delta V is right there. And then we see that the payload we can lift for that specified delta V is smaller than our given payload. And for that given payload, our delta V is again, these are optimized numbers, is smaller. Neither of these, of course, will get you off the Earth, so that's a bummer. All right, and so we see these are optimized numbers. So in this case, what we're doing is obviously the structural coefficient, but we're also taking this payload ratio to be the same, right? And we're playing around with that number to get this optimized thing. So the payload ratio is the design parameter here that they're choosing, and they're choosing it to be the same for all the stages. Right? So the payload ratio, right, is 0.07 here for a single stage, right, 0.34, and then 0.68, and that's just for multiple stages, right? You need a larger payload ratio because you're lifting up other stages, right? What's interesting, of course, here is that the higher payload ratio seems to be better at maximizing delta V, and a slightly lower one seems to be good at maximizing payload. I don't know why that is. And of course, if lambda and epsilon are fixed, that of course means that Z is fixed because that's just a function of those two numbers. All right, so we've reached the more or less the end of this lecture. We'll just wrap up with a little movie, right? ICBM illustration from, I forget where this one come from. It doesn't say. This is the Minuteman 3 ICBM, illustrating very dramatically the end of the world or whatever. Ignition, right? Again, right off the bat, trying to get horizontal to gravity, so that perpendicular to gravity, so it's not wasting fuel. 19 seconds. Sorry, maybe back it up there. 19 seconds has reached Mach 1. We're at 8,000 altitude. Pressure decreasing. You can see expansion there getting worse. 39 seconds, Mach 3. 38,000 feet. We're essentially in space. Mount Everest anyway. We're doing a roll here. First stage separation. We've lost our structural mass. Again, this is not a very well expanded rocket. I would assume we would do better. It's not putting itself into parking orbit, mind you. It's like it will re-enter shortly. We've lost our adapter. We've lost our fairing as well because we're in space. We don't need that fairing anymore. Losing our second stage. Now here's our third stage. Third stage is separating out. I forget what the timing is here. Here we've got our upper stage. The only thing attached to the upper stage, right? We've got the upper stage rocket. But the only payload actually attached to this stage is the warhead itself. So the upper stage doing some maneuvering thrusters, pointing the payload towards its reentry attitude. It's going to spin it up, right, and then release it. So then the upper stage backs off, and just the warhead goes ballistic, spinning itself up at the right attitude. And of course, once it's spun up, it's not going to be able to change attitude, so it needs to be at the right direction to enter the atmosphere directly head on. It's getting very warm there. And then of course it's gonna, I don't know, we don't need to, I don't know, dioff.org. Okay, that's where this came from. Okay, so in conclusion, how do we get into space, right? Oops. Is rockets. Hopefully this lecture gives you some idea of the limitations of delta V and why it's just so expensive to produce delta V. We spend most of our rocket, most of the mass of the rocket, just putting ourselves into orbit, that 9.8 kilometers per second, which even that, just getting into orbit requires staging. You can't do it without staging. And then of course, if you need delta V to get to Mars or what have you, well, there's this exponential increase in the total mass of your rocket. Oops, I guess I should be using my pen. That's why we haven't. We have an exponential increase in the required mass of the rocket for as a function of total delta V budget. Right, and that's with staging, right? So if you have that's without structural mass. If you add structural mass in, then this would be the continuous staging case, and so this number just like it becomes unreasonably sorry. The rocket just can't support that much payload. We've 11 million pound rocket to get a relatively small payload to get Elon Musk's convertible into space, right? I think it was going to the sun or something. Right. Here's Elon Musk's convertible. Anyway, gives you some appreciation for the delta V, maybe some appreciation for like why we're so interested in alternative forms of lift, such as say space elevators, right? Space elevator launch system and so forth. So now, given these delta V's, in the next lectures we'll talk about orbital perturbations, why that delta V budget is needed, and then finally we'll come to we'll come to interplanetary mission planning, and finally spacecraft design. Okay, so I'm going to end this lecture here, which I apologize has gone on rather long.